When we launched the James Webb Space Telescope on Christmas Day 2021, humanity was essentially saying one thing to the universe: show us your secrets. And boy, did it listen. You see, there's something profoundly unsettling about looking too far into space. It's not just about seeing distant objects. It's about witnessing what those objects tell us about reality itself. The James Webb has been doing exactly that, and what it's found has fundamentally challenged some of our most cherished assumptions about how the cosmos works. Let me be direct with you. Space is far more crowded, far more violent, and far more mysterious than we ever believed. And the James Webb didn't just peer deeper than any instrument before it. Peered so deep that it's forcing us to completely rewrite the textbooks we've been teaching from for decades. The observations are so disturbing, so contrary to our expectations, that we're now facing what scientists call a paradigm crisis. We have observations that don't fit our models. Multiple observations, consistent observations, systematic observations across the entire early universe. This is not about a few outliers or measurement errors. This is about the fundamental nature of how we understand cosmic evolution. When the James Webb looked deep into space, it looked so far that it peered back to a time when the universe was less than 1 billion years old. In astronomical terms, that's the cosmic infancy. That's when the universe was still a baby, still learning how to be a universe. And what the James Webb found in that cosmic infancy is deeply wrong. Not wrong in the sense of evil or immoral, wrong in the sense of contradicting everything we thought we knew about how structure forms in the universe. The galaxies it found shouldn't exist. The black holes shouldn't be there. The amount of activity, the level of violence, the sheer productivity of the early universe, none of it matches what our models predict. Think about what that means for a moment. We've spent decades, literally decades, building models of cosmic evolution. We've used supercomputers with processing power that would have seemed like magic to scientists 50 years ago. We've incorporated everything we know about physics, gravity, dark matter, dark energy, stellar evolution, and nuclear fusion. We've tested these models against observations. We've refined them. We've published thousands of papers in peer-reviewed journals. And then the James Webb comes along and says, yeah, none of that accounts for what's actually happening. That's not a minor correction. That's not a small adjustment to parameters. That's a wake-up call that something fundamental about our understanding is wrong. Part 1. The tools of discovery, the Hubble legacy, and its limitations. To truly understand why the James Webb's discoveries are so disturbing, we need to start with the tool it replaced as humanity's primary window into the distant universe: the Hubble Space Telescope. The Hubble was revolutionary. When it was launched in 1990, it transformed our understanding of the cosmos. It gave us the first accurate measurements of the expansion rate of the universe. It showed us galaxies as they were billions of years ago. It discovered that supermassive black holes lurk at the centers of galaxies. It revealed that the expansion of the universe is accelerating. Without Hubble, we wouldn't have our current cosmological model. But Hubble has limitations. It observes primarily invisible light, the wavelengths that human eyes can see. That's fine for nearby objects, but for the most distant objects, there's a problem. The universe is expanding, which stretches the wavelengths of light coming from distant objects. Light that started out in the visible part of the spectrum gets shifted toward infrared wavelengths. Imagine trying to look at something through a thick fog while wearing glasses that only work in visible light. You can see some things, but much of what you're trying to observe is obscured. That's essentially what Hubble faces when trying to look at the most distant galaxies. Moreover, dust, those clouds of tiny particles that form from the remnants of exploded stars, absorbs visible light. In the modern universe, dust is a significant component of many galaxies, and it fills the space between galaxies. When you're trying to look at distant, dusty galaxies through Hubble's visible light eyes, much of the light gets absorbed before it reaches the telescope. The James Webb, on the other hand, observes primarily in infrared wavelengths. Infrared light can penetrate dust clouds that would be opaque to visible light. It's like giving someone night vision goggles. Suddenly, they can see through darkness and haze. But that's just one advantage. The James Webb is also significantly larger than Hubble. Its primary mirror is about 6.5 meters in diameter, compared to Hubble's 2.4 meters. That greater size means greater collecting area, which means it can gather more light from distant, faint objects. It's the difference between looking at stars with binoculars versus looking at them with a large telescope. And the James Webb's infrared detectors are incredibly sensitive. They can detect photons, individual particles of light, with extraordinary precision. This allows astronomers to measure the properties of very faint, distant objects that would be invisible to Hubble. The combination of these factors, larger mirror, infrared sensitivity, incredible detector sensitivity, gives the James Webb a window into the universe that is qualitatively different from what Hubble could provide. It's not just seeing further. It's seeing a completely different aspect of the universe. The redshift revolution. To truly understand what the James Webb is revealing, we need to understand something called redshift. This is crucial to everything we're about to discuss, so let me explain it carefully. In the early 20th century, astronomers observed that the light from distant galaxies was shifted toward longer wavelengths, toward the red end of the spectrum. This phenomenon is called redshift. The Austrian physicist Christian Doppler had proposed a century earlier that waves from moving sources would be shifted in frequency depending on whether the source is moving toward or away from the observer. This is why the siren on an ambulance sounds different in pitch as it approaches and then recedes from you. For galaxies, the redshift is caused by the expansion of the universe itself. Space is expanding everywhere, stretching the wavelengths of light traveling through it. The further a galaxy is away from us, the more the universe has expanded while that galaxy's light was traveling toward us, and the more that light's wavelengths have been stretched. Astronomers measure redshift as a number, usually represented as z. If a galaxy has a redshift of z equals 1, that means its light has been stretched by a factor of 2. If it has a redshift of z equals 10, the light has been stretched by a factor of 11. Here's the critical part. By measuring redshift, we can determine how far away a galaxy is. And because light takes time to travel, a galaxy that is far away is being observed as it was in the distant past. If a galaxy is so far away that its light took 13 billion years to reach us, we're seeing it as it was 13 billion years ago. The James Webb has identified galaxies at redshifts of z equals 11, z equals 13, z equals 14, and beyond. These are incredibly distant objects, being observed as they were when the universe was very young, only a few 100 million years old. This is where the disturbing discoveries begin. Part 2. The Impossible Galaxies, JADES, GS Z14-0. The galaxy that shouldn't exist. Let me tell you about the discovery that really started the paradigm crisis. In September 2023, astronomers announced the discovery of what they call JADES, GS Z14-0. The name is a mouthful, but it breaks down as follows. JADES refers to the survey it was found in the Jacobs et al. Deep Extragalactic Survey. GS means it's a galaxy/star. Z14-0 indicates its redshift is approximately 14.3. Now, what does redshift 14.3 mean? In terms of cosmic time, the universe is approximately 13.8 billion years old. A redshift of 14.3 corresponds to looking back in time to when the universe was only about 290 million years old. 290 million years. That's less than 1% of the current age of the universe. For comparison, 290 million years ago on Earth, dinosaurs were just beginning to evolve. Insects hadn't yet developed wings. The continents looked completely different from how they appear today. In the context of Earth's history, 290 million years is an enormous span of time. But in the context of the universe's history, it's a cosmic blink of an eye. And yet, JADES GS Z14-0 is a massive galaxy. When astronomers measured its stellar mass, the total mass of all the stars contained within it, they found it contains roughly 200 billion stars. That's comparable to the Milky Way. Our Milky Way is the product of 13.8 billion years of cosmic history. It's had time to accumulate stars through numerous processes: initial star formation, mergers with other galaxies, accretion of smaller galaxies over billions of years. But JADES GS Z14-0 achieved comparable stellar mass in only 290 million years. That's a difference of a factor of nearly 50. The early galaxy had to form stars nearly 50 times more efficiently than our galaxy has managed over its entire history. When this discovery was announced, it sent shockwaves through the astronomical community. This wasn't supposed to happen. According to our lambda-cold dark matter model, the standard model of cosmology that we've been using for decades, galaxies in the early universe should be small and simple. They should grow gradually by accumulating stars over time, building up from small beginnings to larger structures. But JADE's GS-Z14-0 is large and complex, and it appeared far too early in cosmic history. Initially, some astronomers thought there might be a measurement error. Perhaps the distance measurement was wrong. Perhaps the stellar mass estimate was off. So independent teams of astronomers looked at the data again, using different methods, different wavelengths, different analysis techniques. The results confirmed the initial findings. JADE's GS-Z14-0 is indeed at redshift 14.3. It is indeed very distant, and it does indeed contain roughly 200 billion stars. But JADE's GS-Z14-0 is not alone. A systematic pattern emerges what makes the discovery of JADE's GS-Z14-0 truly disturbing is not the discovery itself, but what came after. In the months following its announcement, astronomers using the James Webb identified many more galaxies with similar properties. Not just one or two outliers, dozens, hundreds. There's a galaxy at redshift 13.2 that appears to contain a few hundred billion stars. There's another at redshift 12.5 with a similar stellar mass. There's a whole population of unexpectedly large, unexpectedly mature galaxies in the early universe, all challenging our models. What's particularly striking is that this isn't just happening in one location on the sky. The James Webb has observed multiple regions of the sky with deep surveys, and in every region, it's finding these oversized early galaxies. This suggests it's not a localized phenomenon or a statistical fluke. It's a systematic feature of the early universe. Astronomers have now performed detailed statistical analyses, and the results are clear. The number of massive galaxies at high redshift is at least 10 times higher than our models predict. Some studies suggest it's even higher than that. The abundance is wrong by an order of magnitude or more. Think about what that means. When our model predicts that there should be one massive galaxy in the early universe, the James Webb is finding 10. When the model predicts there should be 10 galaxies, we're finding 100. That's not a small discrepancy. That's a fundamental failure of our understanding. The formation challenge: so how did these galaxies form so quickly? Let's do some calculations to understand the scale of the problem. To form 200 billion stars in 290 million years, you would need to form approximately 690 million solar masses of stars every single million years. Every year, the equivalent of millions of suns need to condense out of gas and form new stars. For nearly 300 million years in a row, without significant pause or interruption. For comparison, the Milky Way today forms roughly 2 solar masses of new stars per year. That's a pittance. At that rate, it would take the Milky Way about 100 billion years to accumulate 200 billion solar masses of stars. And the Milky Way's star formation rate has actually been quite a bit higher in the past, especially in its first billion years. But even accounting for that, the early universe galaxies appear to be forming stars at rates that are orders of magnitude higher than what we see in modern galaxies. How is that physically possible? Star formation is a process where gas clouds collapse under their own gravity, compressing and heating until nuclear fusion ignites in the cores of newly formed stars. This process is constrained by several factors: the amount of gas available, the rate at which gas can cool and collapse, the feedback processes that prevent or limit star formation, and the efficiency with which stars can form from available gas. In modern galaxies, star formation is actually quite inefficient. When a galaxy forms, only a small fraction of its gas becomes stars. Much of it remains as interstellar gas, which gradually becomes more difficult to convert into stars as the gas heats up and spreads out. But the James Webb observations suggest that in the early universe, star formation was far more efficient. Galaxies were converting much larger fractions of their available gas into stars, and they were doing it very quickly. What could cause such efficient star formation? Several possibilities come to mind, none of them comforting. First, maybe the physics of star formation was different in the early universe. Perhaps conditions were such that gas could collapse into stars more readily, or perhaps the stellar masses that formed were different, or perhaps multiple generations of stars formed and died very rapidly, enriching the gas with heavy elements that made star formation more efficient. Second, maybe dark matter played a different role. Dark matter is the invisible substance that makes up about 85% of all matter in the universe. It creates the gravitational scaffolding on which galaxies form. Perhaps in the early universe, dark matter's interaction with normal matter was different, facilitating faster structure formation. Third, maybe the initial conditions in the early universe were different from what we assumed. Perhaps the density fluctuations that grew into structures were larger or more developed than we thought, allowing structure to form faster. Fourth, maybe the universe itself is older than we think, and there was simply more time for structure to form than our current age estimate suggests. None of these possibilities are particularly comforting, because they all imply that something fundamental about our understanding is wrong. The morphology mystery adding to the puzzle is another observation that's equally disturbing. Many of these early galaxies have complex, well-defined structures. Galaxies come in different shapes. There are spiral galaxies like the Milky Way, with graceful spiral arms wrapped around a central bulge. There are elliptical galaxies, which are more spherical or elongated. There are lenticular galaxies, which have a disk-like spirals but lack the spiral arms. There are irregular galaxies that don't fit neatly into any category. These different shapes tell a story about a galaxy's history. Spiral galaxies typically have relatively quiet histories. Their disk structure indicates they've had time to settle into a stable configuration. Elliptical galaxies are often the result of collisions and mergers that have jumbled up the structure. Irregular galaxies are usually disrupted by interactions with other galaxies. In the modern universe, the morphologies of galaxies are the result of billions of years of cosmic evolution. Disks form as gas gradually settles into stable configurations. Mergers happen and reshape galaxies. Gravitational interactions with neighbors can disrupt galactic structures. But when astronomers use the James Webb to observe high-redshift galaxies in the early universe, they find something unexpected. These young galaxies often have well-defined structures. Some appear to be disk galaxies with organized structure. Some appear to be elliptical galaxies. The diversity of morphologies is surprisingly similar to what we see in the nearby universe. This raises a profound question. How did galaxies develop such organized structures so quickly? How did disk galaxies form their flat, organized disks when they've only had a few 100 million years to do so? How did elliptical galaxies develop their smooth structures? In the modern universe, such structures take billions of years to develop. The formation of a disk galaxy requires that gas gradually settle into a disk configuration through dissipative processes. This takes time. The formation of an elliptical galaxy typically requires a merger, which takes time for the dynamical relaxation to occur. But in the early universe, these processes appear to have happened much faster. Either the physics of structure formation was different, or the timescales were different, or something we don't understand is at work. The dust problem here's another piece of the puzzle that adds to the disturbance. Dust. The universe contains dust, clouds of tiny particles formed from the remnants of exploded stars. Dust is important in astronomy because it absorbs and scatters light. When we observe a distant galaxy, if there's dust between us and that galaxy, the light gets dimmed and reddened. In the modern universe, dust is a major component of many galaxies. Our own Milky Way has a distinctive dark band across the sky caused by dust clouds in the galactic plane. Dust takes time to build up. It forms from the ejecta of supernova explosions and the winds of dying stars. To have significant quantities of dust, you need to have had many stellar deaths and many supernova explosions. In the early universe, there shouldn't be much dust initially. The early universe had only been around for a few 100 million years. There hadn't been time for many stars to form, age, and explode. There hadn't been time for dust to accumulate. Yet the James Webb has found evidence of significant dust quantities in high redshift galaxies. Some of these galaxies contain hundreds of millions of solar masses of dust in the early universe. Enough dust to be detected despite being at redshifts greater than 10. How did this dust form so quickly? The implications are staggering. To have that much dust, there must have been many stellar deaths. That means there must have been many generations of stars that formed, lived out their lives, and exploded. That means the star formation rate must have been extraordinarily high. But wait, earlier we talked about the star formation rates needed to form 200 billion solar masses of stars in 290 million years. Those rates are already extraordinarily high. Adding the requirement that many of these stars also needed to die and enrich the galaxy with dust pushes the scenario even further into the realm of the seemingly impossible. Unless, of course, these galaxies really did undergo star formation at such ferocious rates. Unless the early universe really was that violent, that productive, that different from the modern universe. Part 3. The black hole crisis. Supermassive black holes that shouldn't exist if the existence of unexpectedly massive galaxies at high redshift is disturbing. Then the discovery of supermassive black holes in the early universe is absolutely alarming. A supermassive black hole is an object of incomprehensible density and mass. It's a region of space where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. Our own Milky Way harbors a supermassive black hole at its center called Sagittarius A*, which contains about 4 million times the mass of our Sun. The galaxy M87, which is much larger than the Milky Way, harbors a black hole with a mass of about 6.5 billion solar masses. Supermassive black holes are thought to form through a specific process. It starts with a stellar mass black hole, the remnant of a massive star that exploded as a supernova. These stellar mass black holes typically have masses between 5 and 20 times that of our Sun. Then, according to the theory, this black hole grows by consuming matter from its surroundings and by merging with other black holes. The growth of a black hole through accretion is limited by something called the Eddington limit, named after the physicist Arthur Eddington. When matter falls into a black hole at high speeds, it heats up tremendously through friction. This heat is converted into radiation that streams outward. At a certain point, the radiation pressure becomes so strong that it blows away the incoming material, preventing further accretion. The Eddington limit can be exceeded through super-Eddington accretion, which can happen when a particularly dense accretion disk is funneling material into the black hole faster than the radiation can push it away. But even with super-Eddington accretion, there are limits. The bottom line is that black holes have a maximum growth rate. They can't grow infinitely fast. If you start with a 10 solar mass black hole and you feed it at the theoretical maximum rate for billions of years, it might grow to be 1 billion times more massive. But getting from 10 solar masses to 1 billion solar masses in only a few 100 million years seems impossible according to our understanding of accretion physics. Yet the James Webb has found evidence of exactly this happening. ULA's J1342 plus 0928. The billion solar mass quasar. Let me tell you about a specific object that really epitomizes the black hole growth problem. ULA's J1342 plus 0928. This is a quasar, an active galactic nucleus that we observe as it was pointing somewhat toward us, so we see the brilliant radiation from the accretion disk and jets. ULA's J1342 plus 0928 existed when the universe was only about 690 million years old. And the black hole at its center has a mass of approximately 800 million solar masses. 800 million suns, all compressed into a point. Now let's do the math. If this black hole started as a 10 solar mass stellar mass black hole and grew at the Eddington limit, how long would it take to reach 800 million solar masses? The calculation shows it would take approximately 1.3 billion years. Maybe a bit less if the black hole started with a larger seed mass or if it experienced periods of super-Eddington accretion. But the basic timescale is around 1 billion years. And yet, this black hole existed when the universe was less than 700 million years old. The timeline doesn't work. The arithmetic doesn't add up. According to our understanding of black hole growth, this object shouldn't be able to exist. But it does. The James Webb has observed it. Multiple independent observations have confirmed its properties. It's real. This discovery is deeply troubling because it suggests that either our understanding of black hole growth is incomplete, or the universe is older than we think, or something else entirely is going on that we haven't accounted for. The prevalence of early supermassive black holes ULA's J1342 plus 0928 is not alone. In fact, it's not even unusual. The James Webb has revealed that supermassive black holes in the early universe are far more common than previous surveys suggested. Before the James Webb, astronomers had identified a handful of quasars at high redshifts. These were notable precisely because they seemed rare. Finding even 1 billion solar mass black hole at a redshift greater than 6 was considered a significant discovery. But the James Webb has changed that. Surveys using the James Webb have identified dozens of black holes in the early universe that contain hundreds of millions to a few billion solar masses. The abundance of these objects is much higher than previous estimates suggested. This raises a profound question. If supermassive black holes were abundant in the early universe, that means black hole growth must be much more efficient than we thought. Either black holes grow faster than our models predict, or the seeds that form supermassive black holes were much larger and more numerous than we assumed, or there's something about the physics of black hole accretion in the early universe that's fundamentally different from what we understand today. Active galactic nuclei everywhere adding to the problem is another observation. Many of the galaxies observed by the James Webb in the early universe appear to host active galactic nuclei, supermassive black holes that are actively consuming matter and radiating enormous amounts of energy. In the modern universe, active galactic nuclei are relatively rare. Only about 10% of galaxies at any given time contain AGN. Most supermassive black holes are in a quiescent state, not actively feeding. But in the early universe, the James Webb has found that AGN appear to be far more common. Some surveys suggest that up to 20% or even higher of the galaxies at high redshift contain AGN. That's 2 to 3 times more common than in the modern universe. If AGN were this prevalent in the early universe, that has enormous implications. It means the universe was a far more violent, far more energetic place. It means that supermassive black holes were actively feeding on their galaxies at much higher rates. The energy released by AGN is immense. An active galactic nucleus can outshine an entire galaxy containing hundreds of billions of stars. If such objects were common in the early universe, the universe would have been filled with brilliant light sources pumping enormous amounts of energy into their surroundings. This energy has consequences. AGN produce jets of relativistic particles that can travel across vast distances. They heat the gas in their host galaxies, preventing it from cooling and forming new stars. They can blow gas completely out of galaxies. In general, AGN feedback is thought to be a crucial process that limits galaxy growth. If AGN were more common in the early universe, then AGN feedback would have been stronger. This would have worked to suppress star formation and limit galaxy growth. Yet we observe that galaxies were growing rapidly and forming stars prolifically. This seems contradictory. How can galaxies grow rapidly when AGN feedback is suppressing their growth? The answer might be that the early universe had much more gas available, allowing galaxies to overcome the limiting effects of AGN feedback and continue growing. Or it might be that AGN feedback was less effective than we think. Or it might be that something about the early universe made galaxies more resistant to the effects of AGN feedback. Whatever the answer, it's clear that AGN were playing a major role in the early universe, a role that's different from their role in the modern universe. The quasar population explosion. The James Webb has found so many quasars at high redshifts that astronomers have started to revise estimates of the quasar population in the early universe. Before the James Webb, the numbers suggested that quasars were rare at the highest redshifts. Now, with the James Webb data, it appears that quasars were more abundant than previously thought. Some of the most recent analyses suggest that the quasar number density might be several times higher than previous estimates. This abundance has implications beyond just black hole growth. It suggests that the conditions necessary for black hole feeding were more common in the early universe. It suggests that the early universe provided favorable circumstances for black holes to grow rapidly. What made the early universe so favorable for black hole growth? Possible explanations include higher gas densities, providing more material for black holes to consume, higher temperatures, which might affect how efficiently black holes can feed, more frequent galaxy mergers, which might funnel gas into black hole accretion disks, different composition of the intergalactic medium, which might affect accretion processes, different properties of dark matter, which might affect how gas flows toward black holes. Each of these explanations would represent a significant difference between the early universe and the modern universe. Part 4. The timeline problem. The age of the universe in question. One of the most fundamental facts about the cosmos is its age. We believe the universe is approximately 13.8 billion years old, based on multiple independent measurements. This age estimate comes from several sources: the cosmic microwave background measurements, the properties of globular clusters, the properties of type Ia supernovae, the expansion rate of the universe. All of these measurements point to an age of roughly 13.8 billion years, with an uncertainty of roughly 100 million years. This agreement across different measurement techniques is reassuring. It suggests that our age estimate is robust. But it also means that if one of these techniques is giving us the wrong answer, we might not know. The James Webb observations are creating a tension in this picture. Some of the observations suggest that the universe might be older than 13.8 billion years. Let me explain how this tension arises. Stellar ages in globular clusters. One way astronomers estimate the age of the universe is by determining the ages of the oldest stars. If we can find the oldest stars, and if those stars formed early in the universe's history, then the universe must be at least as old as those stars. One place to find very old stars is in globular clusters, spherical collections of hundreds of thousands to millions of stars that orbit the edges of galaxies. The stars in globular clusters formed at roughly the same time, and they all have similar compositions. This makes them ideal laboratories for studying stellar evolution and determining ages. Astronomers have developed techniques for estimating the ages of stellar populations by examining their colors and brightnesses. Young stellar populations emit more ultraviolet and blue light because they contain many massive, hot stars. Older stellar populations emit more red and infrared light because the massive stars have died, leaving behind only low-mass stars. The James Webb has observed some globular clusters and determined the ages of the stars within them, and the results are troubling. Some globular clusters appear to have stellar ages that exceed 14 billion years. Some estimates go as high as 14.5 or even 15 billion years. Wait, how can stars be older than the universe? There are a few possibilities. The first is that the stellar age estimates are wrong. Stellar age estimates are notoriously difficult and rely on computer models of stellar evolution that contain uncertainties. The colors and brightnesses of stars depend not just on their ages, but also on their compositions, their masses, and other factors. When we fit models to the observed colors and brightnesses, there's always some uncertainty. The second possibility is that these globular clusters formed earlier than we thought, perhaps even before the Big Bang in some exotic scenario. This seems unlikely and would require a complete overhaul of our understanding of cosmology. The third possibility, and the one that many astronomers consider most plausible, is that the universe is older than 13.8 billion years. If the universe were, say, 14.5 or 15 billion years old, then globular cluster ages of 14 billion years would be perfectly consistent. This would give the stars time to form and age. But here's the problem. Our other age measurements all point to 13.8 billion years. The cosmic microwave background measurements suggest an age of 13.8 billion years. The supernova measurements suggest an age of 13.8 billion years. The expansion rate measurements suggest an age of 13.8 billion years. If the globular cluster ages suggest the universe is older, while all the other measurements suggest it's 13.8 billion years old, then something is wrong. Either the stellar age estimates are off, or one of the other techniques is giving us the wrong answer. This tension is relatively small. It's a difference of perhaps 500 million to 1 billion years out of a total age of 13.8 billion years. But it's a tension nonetheless, and the James Webb's observations have made it more acute. The reionization epoch shifts. Another piece of evidence that the timeline might be off comes from studying when the universe's hydrogen was ionized. In the early universe, for the first 380,000 years, the universe was filled with a hot plasma. Then, as the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms. The universe became neutral and largely transparent to visible light, though still dark because there were no significant light sources. For hundreds of millions of years, the universe remained neutral and dark. But then stars began to form. The most massive and luminous stars emitted ultraviolet light that ionized the neutral hydrogen back into plasma. Gradually, more and more stars formed, and more hydrogen was ionized. The process of reionization spread across the universe until, eventually, the entire universe became ionized again. The question is, when did this reionization complete? How long did it take? What powered it? These questions are important because the answers tell us about the early universe's star formation history. More efficient star formation would lead to faster reionization. Higher densities of stars would produce more ultraviolet light and ionize the universe more quickly. The cosmic microwave background carries imprints of the ionization state of the universe at different times. By analyzing the polarization of the CMB, astronomers can determine when reionization occurred. The results from the Planck satellite, which observed the CMB with unprecedented precision, suggest that reionization was about 50% complete by a redshift of 6.5 and fully complete by a redshift of 6. Wait, let me convert that to cosmic time. A redshift of 6.5 corresponds to a time when the universe was about 550 million years old. A redshift of 6 corresponds to a time when the universe was about 950 million years old. So reionization appears to have occurred between 550 million and 950 million years after the Big Bang. But here's the problem. The James Webb observations of galaxies suggest that there weren't enough stars in the early universe to produce all the ionizing radiation needed for reionization according to our models. If we count the galaxies the James Webb has found and estimate how much ionizing radiation they would produce, we don't get enough radiation to account for the reionization epoch indicated by the CMB. Either there are more galaxies than we're observing, or each galaxy produces more ionizing radiation than we thought, or reionization was powered by something other than galaxies. This is another piece of evidence that our understanding of the early universe is incomplete. What if the universe is older? Some cosmologists have speculated that resolving these tensions might require that the universe is older than 13.8 billion years. If the universe were, say, 15 billion years old, that would give more time for galaxies and black holes to form and grow. It would give more time for reionization to occur. It would resolve some of the timeline issues we've been discussing. But changing the age of the universe isn't a simple solution. The age estimate comes from multiple independent techniques, all of which point to 13.8 billion years. If the universe is actually older, it would mean that something is systematically wrong with these measurement techniques. For example, if the expansion rate of the universe is measured incorrectly, that would affect the age estimate. If the properties of dark energy are different from what we assume, that would affect the age. If the relationship between redshift and distance is different from what we assume, that would affect the age. Any of these changes would represent a profound shift in our understanding of cosmology. So while invoking an older universe might solve some problems, it would create others. The bottom line is that there are timeline tensions in cosmology between the James Webb observations and our other age measurements, and we don't yet have a clear resolution. Part 5. The fundamental physics challenge the paradigm crisis in cosmology in the history of science. Paradigm crises are rare but transformative. A paradigm crisis occurs when observations consistently fail to match predictions, when the standard model breaks down systematically, when the framework we've been using to understand a field of science becomes inadequate. The classic example is the paradigm crisis that led to the development of quantum mechanics. In the late 19th and early 20th centuries, physicists found that the classical physics of Newton and Maxwell couldn't explain certain phenomena. The behavior of light, the properties of atoms, the radiation emitted by hot objects. These observations forced physicists to develop an entirely new framework, quantum mechanics, which has proven incredibly successful. Another example is the paradigm crisis that led to Einstein's theory of relativity. Newton's mechanics and Maxwell's electromagnetism, which had been the foundation of physics, turned out to be incomplete when applied to very fast-moving objects or very strong gravitational fields. Einstein developed new theories that preserved what was correct in the old theories while extending them to new regimes. We might be entering another paradigm crisis, this time in cosmology. The James Webb observations are revealing that our standard lambda cold dark matter model is incomplete. Not just slightly incomplete, but systematically incomplete. Nearly every major class of observations in the early universe is telling us that something is wrong with our model. What needs to change? If the lambda CDM model is incomplete, what needs to be changed? There are several possibilities. First, our understanding of galaxy formation might be incomplete. Perhaps we don't understand how efficiently galaxies can form stars. Perhaps we're missing feedback mechanisms that enhance or suppress star formation. Perhaps dark matter plays a more active role in galaxy formation than we currently assume. Perhaps the initial mass function of stars, the distribution of stellar masses, was different in the early universe than it is today. If galaxy formation physics is different from what we think, that could explain why galaxies grew so rapidly and efficiently in the early universe. It could explain the high star formation rates. It could explain the rapid accumulation of stellar mass. Second, our understanding of black hole formation and growth might be incomplete. Perhaps black holes can grow faster than we thought. Perhaps there are mechanisms for black hole accretion that we haven't accounted for. Perhaps intermediate mass black hole seeds form more readily than we assumed. Perhaps the early universe had conditions that favored rapid black hole growth. If black hole physics is different from what we think, that could explain the abundance of supermassive black holes at high redshift. It could explain the prevalence of AGN in the early universe. Third, the early universe might have had different physical laws or initial conditions. Perhaps the fundamental constants of nature were different in the early universe. Perhaps gravity worked differently. Perhaps dark matter had properties we haven't accounted for. Perhaps dark energy had different properties. Perhaps the universe underwent inflation or other processes that created different initial conditions than we assume. If the physics of the early universe was fundamentally different, that could explain all the anomalies. But it would also require us to understand what made the early universe different and why it changed to the physics we see today. Fourth, our measurements and observations might be systematically wrong in ways we haven't recognized. Perhaps our redshift measurements are systematically off. Perhaps our stellar mass estimates are systematically biased. Perhaps there are observational systematic errors that affect multiple telescopes and techniques. This is always possible in science, but given that the James Webb observations have been confirmed through multiple independent methods, this seems less likely. Fifth, the universe itself might be different from what we think on a fundamental level. Perhaps the Big Bang was not the beginning, and the universe is older than we think. Perhaps there's a cyclic universe in which universes are born and die and are reborn. Perhaps there's a multiverse with multiple universes having different physical laws, and we happen to observe the universe we're in because it has the physics necessary for observers to exist. Perhaps time itself works differently than we assume. These ideas are more speculative, but they can't be dismissed out of hand. The role of dark matter, a key player in all these discussions, is dark matter. Dark matter makes up about 85% of all matter in the universe. We know it exists because of its gravitational effects. Galaxies rotate in ways that suggest there's more mass than we can see in stars and gas. But we don't know what dark matter is. Dark matter could be WIMPs, weakly interacting massive particles. Could be axions. Could be sterile neutrinos. It could be primordial black holes formed in the early universe. Could be something we haven't even conceived of yet. The properties of dark matter for galaxy formation. Dark matter provides the gravitational scaffolding on which galaxies form. The distribution of dark matter determines where galaxies will form and how quickly they'll accumulate mass. If dark matter was different in the early universe, if it had different properties or interacted with normal matter differently, that could profoundly affect how structure formed. Could make structure form faster, allowing galaxies and black holes to form and grow more rapidly. Some cosmologists have speculated that dark matter might have had temperature fluctuations in the early universe that created the initial conditions for rapid structure formation. Others have proposed that dark matter interactions with normal matter could be modified to facilitate galaxy formation. These ideas are speculative, but they represent attempts to modify our physical understanding to account for the James Webb observations. Modified gravity? Another possibility is that gravity itself is different from what Einstein described. Most physicists accept Einstein's general relativity as the correct description of gravity, and experimental tests have confirmed it to extraordinary precision. But at the scales we're probing with the James Webb, the very early universe, where the density fluctuations are still developing, there might be modifications to gravity. One proposed modification is called MOND, or Modified Newtonian Dynamics. MOND suggests that gravity works slightly differently at very low acceleration regimes. If MOND is correct, it would change how structures form in the universe, potentially allowing faster growth. Other modified gravity theories have been proposed as well. Some involve extra dimensions. Some involve additional fields. Some involve non-local modifications to gravity. Most physicists are skeptical of modified gravity theories because they seem to introduce unnecessary complexity, and there's no strong observational evidence for them. But if the James Webb observations continue to challenge our understanding of structure formation, modified gravity theories might become more viable. The cosmological constant, one of the great mysteries of cosmology, is the nature of dark energy, represented in the lambda CDM model by the cosmological constant. Dark energy makes up about 68% of the universe's energy density, yet we have no idea what it is. In the modern universe, dark energy's effect is to accelerate the expansion of the universe. But in the early universe, when the density was much higher, dark energy's effect was negligible. Gravity dominated, slowing down the expansion. However, there are theories that suggest dark energy might not be constant. Perhaps it changes with time. Perhaps it's not just a cosmological constant, but something more dynamic. If dark energy was different in the early universe, it could affect how structures form. Some theories propose quintessence, a dynamic form of dark energy that changes with time. If quintessence was stronger in the early universe, it might affect how gravity operates and how structures form. Again, this is speculative, but it represents an attempt to understand the James Webb observations through modifications to our understanding of fundamental physics. Part 6. The specific anomalies, the dust enrichment timeline. One of the most puzzling discoveries the James Webb has made is the presence of significant quantities of dust in high redshift galaxies. Dust is created by stellar processes. When massive stars explode as supernovae, they eject heavy elements into the surrounding gas. These elements condense into dust grains. When stars with strong stellar winds age and lose their outer layers, they also contribute material that can form dust. The formation of dust takes time. The material has to be ejected from stars, has to cool down, has to condense into grains, and has to accumulate into detectable quantities. In the modern universe, it takes billions of years for galaxies to accumulate significant quantities of dust. But the James Webb has found that some galaxies at redshift 10 or higher, galaxies that formed when the universe was less than 500 million years old, contain substantial quantities of dust. Hundreds of millions of solar masses of dust, in some cases. For there to be that much dust, there must have been many stellar deaths. That means there must have been many massive stars that formed, lived out their lives, and exploded. That means the star formation rate must have been extraordinarily high, with a significant fraction of stars being massive. Moreover, the dust formation itself takes time. If the dust was formed through supernova processes, there would need to be time for the supernova ejecta to cool and condense. If the dust was formed through stellar winds, there would need to be time for the winds to accumulate material and for the material to condense. The timeline is incredibly tight. How can this much dust form in less than 500 million years? One possibility is that dust can form more efficiently than we thought. Perhaps under the conditions in the early universe, dust condensation was faster. Perhaps the physics of dust formation is different from what we understand. Another possibility is that the dust came from a previous population of stars that formed very early in the universe's history. But this requires that stars formed at such extreme early times that they would have had even less time to evolve. Or perhaps some of the dust was primordial, formed directly in the early universe through processes that don't operate in the modern universe. The bottom line is that the presence of significant dust quantities in high redshift galaxies remains one of the most unexplained observations from the James Webb. The metallicity problem, metal enrichment in the early universe, presents another puzzle. When astronomers observe the light from distant galaxies, they can measure the presence of elements heavier than helium, what astronomers call metals. The amount of metals in a galaxy is a measure of how many generations of stars have lived and died within it, because each generation adds metals through stellar death and supernova explosions. In the modern universe, there's a relationship between a galaxy's mass and its metallicity. More massive galaxies are more metal-rich. This makes sense. More massive galaxies have undergone more star formation, more stellar death, and more chemical enrichment. But the James Webb has found that, in the early universe, this relationship is scrambled. Some high-redshift galaxies are quite metal-rich despite not being particularly massive. Others are massive but not particularly metal-rich. This suggests that the metallicity didn't build up gradually in lockstep with galaxy mass, as our models predict. Instead, it spiked rapidly in certain galaxies. What could cause such rapid metallicity spikes? The most likely explanation is intense, rapid star formation followed by equally rapid stellar death. If a galaxy undergoes a starburst, a period of intense star formation with many massive stars, and then a large fraction of those massive stars explode as supernovae, the galaxy would be enriched with metals very quickly. This is consistent with the picture of early galaxies undergoing rapid, bursty star formation. But it emphasizes just how violent and productive the early universe was. The size scale problem here's a subtle but profound observation. Some early galaxies appear to be surprisingly large. Galaxies have sizes. The Milky Way is roughly 100,000 light-years in diameter. Andromeda is about 220,000 light-years across. These are enormous structures, but they're the sizes we're accustomed to. When astronomers measure the sizes of very distant, high-redshift galaxies, they're measuring the physical size of the galaxy, the diameter of the stellar population. For the most distant galaxies, determining the size is difficult because the galaxies appear so small on the sky. But when the James Webb has measured the sizes of high-redshift galaxies, some have appeared surprisingly large. Some appear to have diameters of tens of thousands of light-years, comparable to the Milky Way's size. Now, this might not immediately seem like a problem. After all, maybe early galaxies were just large. But think about how galaxies form. When a galaxy first forms from a collapsing gas cloud, the gas is concentrated in a relatively small region. The galaxy then gradually spreads out as stars form and the system reaches equilibrium. A newly formed galaxy should be relatively small and compact. A large galaxy with a diameter of tens of thousands of light-years requires time to grow to that size. The stars need to be distributed across a large spatial region. The galaxy needs to have undergone dynamics that have spread out the stellar population. In the modern universe, galaxies achieve large sizes through billions of years of gradual growth and dynamical evolution. How did early galaxies achieve comparable sizes in only a few 100 million years? One possibility is that early galaxies had more violent dynamics, with more mergers and interactions that rapidly spread out the stellar population. Another possibility is that the initial gas clouds from which early galaxies formed were larger than the gas clouds that form modern galaxies. A third possibility is that the physics of how stellar systems spread out is different from what we understand. Again, each of these possibilities would represent a gap in our understanding. The quasar luminosity function, the luminosity function of quasars, the distribution of quasar brightness, is another observation that challenges our models. In the modern universe, the quasar luminosity function shows that bright quasars are relatively rare and faint quasars are more common. This is the expected pattern. More objects at lower luminosities, fewer objects at higher luminosities. But in the early universe, the James Webb observations suggest that the quasar luminosity function is different. There appear to be more bright quasars than our models predict. The luminosity function appears flatter, more objects at high luminosities. What does this mean? It means there are more powerful AGN in the early universe than we expected. It means the supermassive black holes were more active and more luminous. This ties into the black hole growth problem we discussed earlier. If black holes were more luminous, they were consuming more material and accreting at higher rates. If there are more luminous black holes, the universe was more violent and energetic in the early epochs. Again, we face the question, how did black holes achieve such high accretion rates so early in the universe's history? Part 7. What this means for the future, the next decades of cosmology, the James Webb has revealed profound challenges to our understanding of the early universe. What happens next? The immediate priority is confirmation. The discoveries need to be verified through independent observations using different techniques and different instruments. The James Webb will continue to observe high-redshift galaxies, accumulating more data. Other telescopes are also observing these objects. The Roman Space Telescope, which NASA is developing, will provide complementary observations with different capabilities. The Vera Rubin Observatory will continuously map the sky, discovering new high-redshift objects. Ground-based telescopes like the Extremely Large Telescope are coming online and will provide detailed observations of distant galaxies. As more data accumulates, the picture will become clearer. We'll be able to determine whether the anomalies are truly systematic or whether they're affected by observational biases we haven't accounted for. Simultaneously, theorists will be developing new models and new explanations. They'll be exploring modifications to galaxy formation physics. They'll be investigating new mechanisms for black hole growth. They'll be considering whether the early universe had different physics from the modern universe. Over the next decade or two, we'll likely see significant advances in our understanding. Some of the mysteries will be resolved. New mysteries will emerge. The role of computer simulations play a crucial role in cosmology. Astronomers use sophisticated simulations to model how galaxies form and evolve in a universe with dark matter and dark energy. The James Webb observations will drive the development of new, more sophisticated simulations. Cosmologists will need to modify their simulations to account for the high-redshift galaxies and black holes that the James Webb has found. Some of these simulations will try to tweak existing physics, changing star formation efficiency, modifying black hole growth rates, adjusting feedback mechanisms. Others will explore more radical modifications, like changes to dark matter properties or modifications to gravity. Through trial and error, simulation and observation, the community will gradually converge on a new understanding that accommodates the James Webb observations while preserving the successes of the old models. The philosophical implications beyond the technical implications, the James Webb discoveries have philosophical implications. For decades, cosmology has been moving toward a more complete understanding of the universe. The successes of the Lambda CDM model seemed to suggest that we were getting closer and closer to the truth. The universe seemed comprehensible, but the James Webb has revealed that the universe is more mysterious than we thought. We've encountered phenomena that challenge our models. We've realized that our understanding is incomplete. This is humbling. It's a reminder that despite all our knowledge and all our sophisticated technology, the universe still has the capacity to surprise us. The universe still has secrets, but it's also exciting. It opens up possibilities for new discoveries. It suggests that there's something profound waiting to be understood. It indicates that there are frontiers of knowledge that remain to be explored. The search for new physics, the James Webb observations might be pointing us toward new physics. Not just tweaks to existing theories, but genuinely new physical principles that we haven't discovered yet. What could this new physics be? We can only speculate. It might involve the nature of dark matter. It might involve modifications to gravity. It might involve new particles or new forces. It might involve new dimensions or new fundamental symmetries. Throughout the history of science, new observations have led to new physics. The discovery of radioactivity led to nuclear physics. The observation of the cosmic microwave background led to confirmation of the Big Bang. The discovery of accelerating expansion led to dark energy. The James Webb might be pointing us toward the next great discovery in physics. What that discovery will be, we can't yet know. But that's part of the excitement. Part 8. The broader context: how we understand the universe to appreciate how disturbing the James Webb discoveries are. It's worth stepping back and understanding how cosmologists approach the study of the universe. The field of cosmology relies on a few fundamental observations and principles. First, we observe that the universe is expanding. Distant galaxies are moving away from us, and the further they are, the faster they're moving away. This is the Hubble expansion, discovered by Edwin Hubble in the 1920s. Second, we observe that the universe is nearly uniform on large scales. If you average over sufficiently large distances, the distribution of matter is roughly the same everywhere. This is the cosmological principle, the assumption that we're not in a special location in the universe. Third, we observe the cosmic microwave background, the ancient light released when the universe was 380,000 years old. The CMB is nearly uniform, with tiny temperature fluctuations of about 1 part in 100,000. These fluctuations are thought to be the seeds from which all cosmic structure, all galaxies and clusters of galaxies, grew. Fourth, we observe dark matter and dark energy through their gravitational effects. Dark matter comprises the majority of matter, and dark energy comprises the majority of the universe's energy density. Building on these observations, cosmologists have constructed the lambda CDM model. This model describes how the universe evolves from the nearly uniform state we observe in the CMB to the lumpy, structured universe we see today, full of galaxies and clusters of galaxies. The lambda CDM model makes specific predictions about what we should observe at different redshifts. It predicts how many galaxies of each mass we should find, predicts how fast galaxies should grow, predicts how often AGN should occur. It predicts the properties of high redshift galaxies. For decades, observations have largely confirmed these predictions. The model has been remarkably successful. This success has led many cosmologists to believe that we're on the right track, that we're gradually converging on a true understanding of the universe. Then the James Webb came along and started making observations that don't match the predictions. The confidence interval problem, there's a statistical issue that's worth mentioning. When astronomers make measurements, they always have uncertainties. They report not just a single value but a range, a confidence interval that accounts for the uncertainty. For example, an astronomer might report that a galaxy's redshift is 10.5 plus or minus 0.3. This means the true redshift is probably somewhere between 10.2 and 10.8, but 10.5 is the best estimate. Now, when the James Webb finds a galaxy that's unexpectedly large or unexpectedly massive for its redshift, there's always the possibility that the measurement is just at the edge of the confidence interval. Maybe the galaxy is actually not as distant as measured. Maybe it's not as massive as estimated. But this can't be the entire story. The James Webb has found dozens or hundreds of such outlier galaxies. It's unlikely that all of them are measurement errors. It's unlikely that all of them happen to be at the edges of confidence intervals in ways that make them appear more extreme than they are. Moreover, when independent measurements using different techniques confirm these results, it becomes clear that something systematic is happening, not just random measurement errors. The publication bias issue, there's another statistical issue worth considering. Publication bias. Astronomers are more likely to publish surprising results than unsurprising results. A galaxy that matches the model's predictions exactly might never be published. But a galaxy that's unexpectedly large or unexpectedly distant will be published. This publication bias means that the galaxies we hear about are biased toward the surprising ones. It doesn't necessarily mean there's a systematic problem with the model. It might just mean that surprising results get more attention. However, when multiple independent teams of astronomers make surveys of the same regions of sky and find that the high redshift galaxy population is systematically larger and more developed than models predict, it becomes clear that publication bias can't explain the results. The pattern is too systematic. The role of uncertainty in science. Finally, it's worth reflecting on the role of uncertainty in science. Science is not about achieving absolute certainty. It's about progressively refining our understanding, reducing uncertainty, and moving closer to truth. The James Webb observations, despite their troubling nature, represent good science. They're carefully measured. They're verified through multiple techniques. They're published and subjected to peer review. They're contributing to our understanding, even if that contribution is to reveal that our understanding is incomplete. The fact that the observations challenge our models is not a failure of science. It's exactly how science should work. Observations challenge theories. Theories are refined or replaced. New observations are made. The cycle continues. The James Webb is contributing to this process. Yes, it's revealing that our models are incomplete, but that's valuable. It's pointing us toward truth. Conclusion. The disturbing universe and the future. What the James Webb has revealed. The James Webb Space Telescope has looked deeper into space than humanity ever has before. It has peered back to times when the universe was less than 1 billion years old. And what it has found is deeply, profoundly disturbing. It has found galaxies that are far too large, far too developed, far too mature for their age. These galaxies contain stellar masses comparable to the Milky Way, formed in time periods that are factors of 50 shorter than the Milky Way's age. It has found supermassive black holes with masses exceeding 1 billion solar masses, existing when the universe was less than 1 billion years old. These black holes shouldn't exist according to our theories of black hole growth. The timescales don't add up. It has found active galactic nuclei to be far more common in the early universe than expected. The universe was far more violent, far more energetic, far more disturbed by black hole activity than we thought. It has found evidence of rapid chemical enrichment, with galaxies containing significant quantities of metals in their early stages. This suggests rapid, intense stellar death and supernova activity. It has found evidence of substantial quantities of dust at high redshifts, indicating rapid enrichment from supernova activity and stellar processes. It has found that the reionization epoch, when the universe's hydrogen was ionized by stellar radiation, may have occurred faster than our models predict, suggesting more efficient star formation or more luminous stars in the early universe. Each of these observations, individually, might be puzzling but explainable. Together, they paint a picture of an early universe that is fundamentally different from what our models predict. The implications for cosmology. These observations have several implications for cosmology. First, our understanding of galaxy formation is incomplete. The mechanisms by which galaxies form and accumulate stellar mass are not fully captured by our models. Either star formation is more efficient than we think, or feedback processes are different, or there are unknown processes at work. Second, our understanding of black hole formation and growth is incomplete. Black holes can apparently grow much faster than our current theories predict. The mechanisms for rapid black hole growth, or the initial seeds from which black holes form, must be different from what we understand. Third, the early universe appears to be systematically different from our models. It produced structures faster, was more violent, was more active. This suggests that the physics of the early universe might differ from the physics of the modern universe, or that the initial conditions were different from what we assume, or that something fundamental about our framework is wrong. Fourth, our age estimates for the universe might need refinement. The tensions between stellar ages and the universe's age, and between galaxy formation timescales and available time, suggest that our age measurements might need to be reconsidered. The path forward. What comes next? How do we resolve these tensions? The first step is confirmation through additional observations. The James Webb will continue gathering data. Other telescopes will observe the same objects. We'll accumulate a clearer picture of the early universe's properties. The second step is theoretical development. Cosmologists will develop new models that can account for the James Webb observations. These models might involve modifications to galaxy formation physics, black hole growth, dark matter properties, or fundamental physics itself. The third step is reconciliation. We'll need to explain not just the James Webb observations, but also reconcile them with all the other observations that support the current lambda CDM model. We can't throw out all our successful models just because of new observations. We need to find a framework that preserves what works while accounting for the new data. The fourth step is new discoveries. As our understanding evolves, we'll make new observations and predictions. Some of these predictions will be confirmed, others will lead to new puzzles. The process will continue. The nature of scientific progress. It's worth emphasizing that the James Webb's disturbing discoveries represent success, not failure. Science progresses through the accumulation of observations that challenge and refine our understanding. The history of science is littered with paradigm shifts triggered by observations that didn't fit the prevailing models. The shift from Ptolemaic to heliocentric astronomy. The shift from Newton's mechanics to Einstein's relativity. The development of quantum mechanics in response to observations that classical physics couldn't explain. We might be at the beginning of another paradigm shift. The James Webb might be the equivalent of the telescope that Galileo pointed at the sky, revealing a universe more complex than anyone had imagined. It might be the measurement that exposed a fundamental flaw in our understanding. If so, the next decade or two of cosmology will be exciting. New frameworks will emerge. New physics might be discovered. Our understanding of the universe will deepen. The bigger picture, looking at the James Webb's discoveries in the broader context of human knowledge, is humbling. We have built an impressive edifice of knowledge about the universe. We've measured the universe's age, its composition, its expansion rate. We've traced the cosmic history from the Big Bang to the present day. And yet, when we look more carefully, we find that our knowledge has gaps. When we peer deep into the early universe with our most sophisticated instruments, we find that it's more complex than we thought. This pattern repeats throughout science. In biology, despite detailed knowledge of genetics and molecular biology, we're still discovering surprises about how life works. In physics, despite the remarkable successes of quantum mechanics and relativity, we're still searching for a unified theory. In astronomy, despite centuries of observation, we're still finding that the universe contains phenomena we don't fully understand. The universe is vast, complex, and full of mysteries. The fact that we can observe it, measure it, and attempt to understand it is remarkable. The fact that our understanding is incomplete should not be surprising. It should be expected. Why this matters, you might still be wondering why the James Webb's discoveries matter. Why should you care about distant galaxies in the early universe? At one level, the answer is intellectual curiosity. We want to understand the universe. We want to know where we come from, how the universe works, what the laws of nature are. This is a fundamental human drive. At another level, the answer is practical. Throughout history, fundamental research into how nature works has led to practical benefits. Maxwell's equations, derived to understand light, led to the discovery of radio waves and eventually to all modern wireless technology. Einstein's theories of relativity, seemingly pure theoretical physics with no practical application, led to the technology that makes GPS work. Quantum mechanics, which seemed like abstract mathematical physics, led to transistors, lasers, and all of modern electronics. The research into how the early universe works might eventually lead to technologies we can't currently imagine. Understanding dark matter and dark energy might open up new frontiers of physics and technology. But beyond the practical benefits, there's something deeper. Understanding the universe is part of understanding ourselves. We are made of matter that was created in stars. The atoms in our bodies were forged in stellar furnaces. We are, in a very real sense, made of stardust. Understanding how the universe works is understanding how we came to exist. The James Webb's discoveries, though challenging and disturbing, are part of this grand human endeavor to understand the cosmos and our place in it. Final thoughts: the James Webb Space Telescope looked too deep into space. It peered back to times when the universe was less than 1 billion years old. What it found was deeply, profoundly disturbing. But that disturbance is not a sign of failure. It's a sign of success. The James Webb is doing exactly what a great scientific instrument should do, revealing the true nature of the cosmos, unfiltered by our preconceptions, challenging us to expand our understanding. The universe, it turns out, is stranger and more complex than we thought. It formed structure more efficiently, evolved more rapidly, and produced more powerful objects than our models predict. The early universe was a place of incredible activity and rapid development. We don't yet understand how it all happened. We don't yet have a complete picture, but we're working on it. Astronomers around the world are analyzing data, developing theories, and making new observations. Slowly, piece by piece, we're building a new understanding of the early universe. The journey toward understanding the cosmos is far from over. In fact, it might be only just beginning. The James Webb has shown us that there are mysteries waiting to be solved, frontiers waiting to be explored, and truths waiting to be discovered. The universe is full of surprises, and that makes it worth studying.